internet or if the screen isn't sharing.
My bad. That was my bad. I forgot to share the screen and start the video. So I was. Okay, let me start over. So these homework questions here that you can actually see now, I think. I threw the 12 volts on there in order to be able to do the question. So those are the ones I was referring to when you were not seeing any of it. After that, of course, you can solve whatever for everything that's missing. And then in the missing, solving for missing values in circuits, obviously you're not always just given the resistances and the voltage and asked for all of the voltages everywhere and currents everywhere. Sometimes there's little puzzles almost where there's very random things missing. So in this question set here, this ABC was actually for number 30. If that confused you, like it did me when I was doing the solution. So it's like A and B, and then it came to another ABC. But I looked and saw there was obviously, it says find, and then, the way they had organized the textbook, it was just kind of obvious on the page, I guess, in the textbook itself. But the way it got put together here became not as obvious. Anyways, so down here for all of these things, your main idea is to look for pairs of values. There's only one thing missing, and also noticing things like current same everywhere or voltage the same everywhere or whatever's appropriate. And I tend to hunt for this as a first. Yesterday, though, the way the solution went was probably actually easier than what I might have done, because this type of thing, the missing information here or the implied information that the current's the same everywhere, for example, that paid off nicely in the example we looked at yesterday, because it made it so I didn't have to solve for a missing total resistance or a missing, I guess, individual resistance, because the way that question was, I think it was a parallel question. So you have 1 over total resistance equals 1 over R1 and so on. And I think we knew all of the resistances, like the total resistance, and then we were missing one of them. Let's go with this lesson right here. This one. I'll just load up what I'm talking about here. It's the one yesterday where I said, oh, that wasn't what I was going to do first, but I'll go for it with you. And we ran through everything, and it worked, of course, because it's just any valid step leads to another valid step and all the way through until you get all of it solved. Just give me a sec here to get this one loaded. So let me just drop down here to, oh boy, what happened there? Draw this thing. Don't know what that was the one. I think it was this one. So I originally had noticed this, right? That you got the total voltage and you got total current, so you can solve for the total resistance. So there'd be only one thing missing, that'd be R1 would be missing, right? So we could have started with that formula, which was kind of this one here, right? That we could have done. So we could have put in the value for the total resistance and for the R2 and R3, got all those numbers, and then you just solve for that one. That's just kind of an uglier equation to have to work with solving. Instead, we ended up solving mostly just little V equals IRs, which are easier. Okay, so I would maybe add in to the steps listing here, find anything and so on, and then I put like sort of secondary thought here was that plus you'll need to use resistance formula. You'll need to use the resistance formulas. Oh, that's not right. That's not what I was thinking. That's not the. I want to add an or notice implied. Notice implied, or I don't know how to say it, like knowledge. Let's say notice knowledge about voltages and or currents. for example, let me just shrink that down and so on. But that's exactly what we did though in the class, right? We went with I think it was Sarah's suggestion of that, which was perfect. It was great. So for example, e.g. here, Vt equals V1 equals V2 in a parallel circuit, or It equals I1 equals I2, etc. in a series circuit. Right? Those are good things to look for first as well, because it might just give you something easier to work with. Okay. Oh boy. It's doing it again, of course. There we go. I think that fixes it. All right. It's still doing it. There we go. All right, so save that just for my own records here. Yeah, so each of these, like you're really gonna need to just plug your way through them. Like, can anybody, like, how many did we get done? I think I suggested 2 of the series and 2 of the parallel. Was that reasonable? Did that work for you? Looking at the solutions, no one's asking right now.
It worked.
Okay. Okay, so that's good. Keep plugging away at that then. What we got on tap for a schedule here is no Teams meeting tomorrow because I have a doctor's appointment. So I'm saying, complete previously assigned work, which will encompass or include like the missing values and circuits from 11, where you do like the other 2 of each or whatever it is, and I'll use the solutions to help yourself through. And then there will be some numbers here that I wouldn't expect you to get done tonight. But instead you keep working at tomorrow, and again the solutions are going to be posted to be able to help yourself. Okay. I'll likely be available a lot of tomorrow, like later on in the afternoon, but just I don't think I'd be back in time for the. I definitely won't be back in time for the Teams meeting. But if you have questions in the afternoon, ask, and if I'm available, then I'll certainly help you out. All right, so that's stuff out of the way. We're on to solving combination circuits. So a combination circuit. Do you have a handout basically of questions, not a handout that goes along as a note? So your handout for the questions to do with this looks like starts like that on the top of it. Be the next one in your pile, hopefully, if they're somewhat in order. So here we go. So what happens in a circuit like this one here, for example, that's on your sheet that I was just pointing out? We've got these 2 are in parallel, right? And then this one's in series with that. So it's a combination series and parallel circuit. So the idea is if you calculate the combined resistance of this using your parallel resistance, total resistance knowledge, then that would be, we know it would be, for example, less than 9 ohms, right? So maybe then something like 4 ohms or something. Now you've got a 4 ohm in series with another 4 ohm. And so you can be like, then you could calculate, oh, I've got a total resistance of 8. So now I can calculate total current. Follow me through this, okay? Just thinking through it. I think we're okay so far, right? The idea of combining these, getting 4 ohms. And then the idea of combining those, saying 4 is 8. Now we're saying, okay, so now we've got a total resistance known, so I can calculate a total current. Okay, my next step would be to say, oh, wait, then I know the current through this one, so I can get the voltage drop through it. And then my next step would be, oh, I know there's a voltage of 30 total, so if there was 10 on this one, for example, I know there'd be 20 across these. And then knowing there's 20 volts dropped across this branch means there's 20 across this one. I can calculate the current, and 20 across this one, I can calculate the current. So verbally, I just went boom, 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 boom through all of those sequential steps that allow us to solve this this combination circuit. Right? And if that's 2 whirlwind all at once or whatever, we're going to be going through it, of course, for multiple examples. But that's the idea overall. I wanted to give you sort of the big picture of what we're trying to tackle. Because it might be a little hard to understand what I mean when I say these steps along the way here, first, second, third, and so on. Okay. All right, so this circuit here, it's a little sloppy looking, but you can see you've got a 1 ohm in series with a parallel section here that has a 3 and a 2 ohm in series and a parallel with a 4, and then there's a 3 ohm, and there's a 4 ohm. You know, it's just a smattering of resistances that are connected in series and in parallel and so on. Okay, so this one's actually a little bit of a harder example, but again, we'll just keep plugging our way through it and doing logical things. So I tried to make it in a bit of a sequential step-by-step, right, to go along with that verbal version of what I did on that other one just now. So you're going to combine any small combinations of resistances you can. So first, for example, it says, you know, like if there's resistances in series somewhere, then combine them, right? And if there's resistances in parallel somewhere, combine them, right? It's nice to, you don't always have to do it, but I'm going to show the idea of like redrawing the new version of the circuit, because it just kind of makes I think it helps you see what you can do next. But if you said, okay, you know what, these two are in series, for example, so we're going to add them and get 5 ohms. We could redraw the whole circuit with a 5 ohm resistor there. Maybe not worth it. Maybe you do multiple steps and redraw. For example, the 1, the 3, and the 4 are in series. So you can add those. That's going to be 4, 5, 6, 7, 8, right? So you can redraw this with an 8 ohm resistor and a 5 ohm resistor, and then the 4 ohm still. Okay, and that would be a simpler version, and then you can sort of do something next. But that would be reasonable to do all at once. Okay, so that's something we're going to look at doing. What I might do is go down to the actual circuit itself. Now, maybe take a minute to draw that circuit on a page. And this page has what I was mentioning there verbally, just talking about all kind of done, right? So step number 1, you know, might have been to just look locally here and be like, oh, I can add those up. So that's 5. And then I have noted here on the page as well that the 1 ohm, the 3 ohm, and the 4 ohm are in series. And so those can add up to be 8, like I mentioned. And so there, I'll just wait for a minute here.
Sorry, can the R4 go with the R2 and the R3, or are they only allowed to be with each other?
So the R2 and 3 are kind of trapped in a parallel branch, right? And so you can't just pretend that they're not trapped in a parallel situation. And so I'm only going to teach you, coach you to combine things that are obviously just in series with each other, rather than being part of something more complicated.
Okay.
Yep. That's why I'm not including them in it, right? Because otherwise you could do the same with the 4 ohm too, right? The 1, the 4, the 3, and the 6 or 4 or whatever are in series sort of too, but yeah, they're part of a bigger, more complicated thing. So hopefully you have a time for that part there. I'll just slide down a little bit here and show like the simplified version now, right? You've got that 8 ohms of simple series combination, and then you've got the simple series combination there of 5, but then you've got this more complicated, parallel thing where you have a 5 ohm and a 4 ohm. Is it 4 ohm? Yeah, a 5 ohm and a 4 ohm in parallel. And so obviously we're going to deal with that next, and end up with another simplified version of the equation. So so far I feel like I'm just doing this stuff, combining and redrawing. I am going to have a step soon where it's going to be like, oh, if you find a missing, a pair of voltages and resistances and current where you only have one thing missing, then of course you're going to find that missing value. So I'll keep plugging away with simplifying first. So this is probably here, right? Yeah. So this part here, knowing that the 4 ohm and combined 5 ohm total there in parallel would add up with parallel resistance techniques. So I would just do, well, you can tell what it there, that's 0.2, and this is 0.25, so the 0.45 total of adding those up, just getting the decimal version, invert and get what the parallel resistance is there of 2.2 ohms. So here's a redrawn version of that circuit now. We just have an 8 ohm and a 2.2 ohm in series. And so, of course, that's a total of 10.22 ohms. So I don't know if I have it redrawn here, but certainly it could, right? So basically we have this. We have a circuit with 10.22 ohms, and that's really overall what we've got. Undo that. So 10.22 ohms, and then we know that it's 12 volts. And so, of course, this is where we're going to say, oh, V equals IR, right? And looking at this one, I've got total voltages, total resistance, and I can get total current. So this is the one where it's like, I've got this one, and I've got this one, so I can determine that one. That'll be on a page soon here. But I'll just go back and officially reveal that, or leave it revealed, that next step. How am I doing for timing here? Is it, I'm okay? I can go to the next page?
I think I need a bit more time, if that's okay.
Yeah, problem at all. That's why I'm asking. Just let me know when you feel like we can move ahead, please.
I'm good, thanks.
Right on, good stuff. All right, so as I alluded to already here, once you have the total resistance, then yeah, you can just get the total current. And then once you have that total current, then you can go back even to this main original equation. Once you know the total current, then you're going to say, oh, wait, I know the current through here. I know the current through here. I know the current through here, right? So those are all things you can work with then, right? It immediately gives you a whole bunch of stuff you can do. So that means we can get the voltage dropped across this part, and this part. That's what we're going to be doing as a next step after we get that total current. And then if we know the total voltage that's dropped across these three, let's say the total voltage of all these is combined total of like 10 volts. Well, then we know that 2 volts is dropped across this, and 2 volts is dropped across that, right? And that's just going to be piece by piece going through all of this. So that we're going to do next, and then any resistance, yeah, any resistance that has a total current through it, we're going to get the voltage, as I mentioned. So we'll be doing that in the example. Okay, I don't know if you necessarily, I was going to say, I don't know if you necessarily need to write these out, but it's basically you're gaining experience in doing this, right? So maybe writing some of this out helps you refer to it to help you through that learning process. But I'll just pause there for a second. It won't get too long. So in our example, we got to the point where we were ready to do that. So let's go ahead and do that now. So there's the total voltage, total current, total resistance pairing of Ohm's law. And we can calculate out that it is 1.17 amps. Again, all the way through from now on when I'm doing questions, I maybe wasn't doing this before, but I'm keeping as many decimals as reasonable, right? Like basically use my memory recall button on my calculator. Like my calculator has an STO for store. So if I do a number like the 12, well, even actually the 10.22, the 10.22 number might have been rounded anyways, right? 1 divided by 0.45 gives me 2.22222, right? So I'm going to use the 10.2222222 when I do the actual calculation here. So this number in my calculations along the way is actually 10 point. Well, you know what? If I was writing this time around, I've rejigged and put things together to use that I've used in the past, but I would just simply write it as 10.2 with a repeat, and I would calculate it that way. And then when I do 12 divided by 10 point, and I just fire a bunch of twos in the calculator, I get 1.17391. And this is where, you know, I might put it like that for now, but point out that I'm really using 1.17391 dot dot dot, right? It's just annoying to, like, you know, have to write so many decimals along the way, but as much as possible, use your calculator. Once I have that 1.71739, I can hit STO, and then the next time I'm doing a calculation with it, I can say, use the recall, it's RCL button. So there's features on your calculator that you can take advantage of to try and keep more numbers. In the end, we know that we can only trust 3 significant digits, right? But along the way in your calculations, keep a bunch. So we've got the total current, and then the next key step here was noticing that total current goes through R1 and R5 and R6 because of where they are in our main circuit. And so that means we can calculate a V1 and a V5 and a V6. Now I'll give you a little bit of time, of course, to put that together.
So those are the ones in series, right?
Yeah, and that's
Okay.
why, because they're in series, we know that the total current definitely goes through them. Yeah.
Okay.
And they're just in series, nothing fancier, right? So we've got a total current goes obviously through there. A total current goes through here. And a total current goes through here. The issue with the other one, of course, is that the total current divides up into 2 parts, right? So it's not total current through those branches. It's going to split up. Right, so I made a note of that there, that they're in series only, and that's why we're picking those ones. All right, so is that enough time there?
I think it's good.
Awesome. All right, so now we have these voltages. We know out of that 12 volts total, we're dropping 1.7, 3.51, 4.68, you know, the individual values. Well, we know the voltage, the total amount of voltage drop must be 12. And so the rest of the voltage must have been dropped across this branch and this branch. Specifically, the rest of the voltage is dropped across the 4 ohm. And of course, the 2 ohm, the 3 ohm are going to split it proportionally, or like based on their resistance, right? So we're saying, okay, well, we know the voltage adds up. And so I use the symbol V with 2 little parallel lines to show like the voltage across the parallel branch. That's shown on the diagram here too. So when we put our numbers in, we know the 12 equals the 1.17 plus the voltage across the parallel branch plus 3.51 plus the 4.68. And so we just solve for the voltage across the parallel branch. I didn't put a box around that one because voltage across the parallel branch isn't necessarily one that we're going to say, yeah, that's like, you know, one of the ones we're looking for. But it is going to give us, of course, the voltage across the 4 ohm, and that'll be boxed in as an answer I'd be looking for. So I'll give you a bit to get that. see that page again in a bit here. I'm just wondering where I'm at. So I think we're onto this one here. Yeah. So that's what we just did, right? We know the voltages in series add up. And so find the missing parts. This is voltages in series. So there's a parallel piece that's in series with the rest and so on, right? And then step 5 is going to be, so step 5, we look at where we're at on this solution set here. We know all the voltages and everything else. Now that we know the voltage that is across this one, we know voltage, we know resistance, so we can figure out the current that actually flows here, right? So that's going to be our next logical step, figure out the current that flows here. Then, if we know there's 1.17 amps of current total flowing, and let's just say maybe 0.17 amps flows through this bottom branch, then the other 1 amp must flow through the top branch, right? So that's going to carry us through the next couple steps. So let's show those. We're saying, okay, find the voltage, great. Find the current that flows through each branch, which we know, of course, V, and if we know the voltage and the resistance, we can find the current, and then we know the currents add up to the total. It becomes a little bit hard, not necessarily as clear as I want it to be, but in context with doing a question, this is more clear. That's why we're doing it simultaneously like this. All right, so that looks like this. Parallel branch, we know the voltage across this 4 ohm is the 2.64. So right here, we figured out that voltage across the parallel branches is 2.64. So we know that's going to be 2.64 across 4 ohms. So that's this calculation right here. There's the 4 and the 2.64. And so we actually calculated out that 0.66 amps flows through that bottom parallel branch. And then, as I've mentioned already, that the total current is splitting up into 2 parts, right? So one part is 0.66, you can figure out the other part. So now we know that 0.51 amps flows through. Oh yeah, that's sort of the next thing, right? After that, but now we know 0.51 amps flows through the top branch, which I'm not boxing in, but I am going to say, oh, so that means 0.51 amps flows through those 2 resistors. Those 2 loads, those 2, whatever you want to call them.
Mr. Horn, I just got a little mixed up with the numbers there. Step 5, what did you do again?
So step 5 was when I noticed that we had calculated the voltage across the parallel branch system was 2.64. And so I noticed that, okay, that gives me the voltage across the 4 ohm, right? And so if I know the voltage across a 4 ohm resistor, then I know how much current, I can calculate how much current will flow. And so that's this right here. I have the voltage across the 4 ohm because it's the only resistor in that parallel branch. And I've got the resistance of it, 4 ohms. And so I calculated the current that'll go through that branch, which is the current through the 4 ohm resistor, 4 ohm resistor number 4.
Do you not have to add in like the top 2 in the parallel circuit as well?
So the top, we're dealing with the top 2 next, right? So the top 2, you're saying after that, once you figure out that 0.66 amps goes through the bottom branch, then we subtract, to figure out how much goes through the top branch. And then once you have how much current goes through the top branch, then you can calculate the voltages across them afterwards. But now this is where we're at here so far. We just have to calculate the voltages next.
Oh, all right.
Does that make sense? So we figured
Yeah,
out,
that's better.
okay, so we had voltage, we had individual voltages across these guys, right? Follow my mouse here. And so then we said, oh, a total voltage of something being dropped across those. So we were able to figure out that the remaining voltage of 2.64 volts is dropped across the branch. So that then told me the voltage across a known resistor, allowed me to calculate a known current. We can't work with these ones yet as easily because we could, I suppose, we could use the 5 ohm, right? If we use the 5 ohm, then we could figure out how much current goes through this branch. But instead, I'm just going for it and saying, well, if I know 0.66 goes through the bottom, I can figure out how much goes through the top. But I totally could go or here, or I could say the top branch is 5 ohms, right? Let me just double check that. Top branch is a 2 and a 3, it's 5 ohms. And so we'd have V equals IR, and this is for that top branch. We'd have the 2.64 volts. We'd have the current through it that we don't know, and we'd have the resistance of 5. And so we could divide out that 5, and 2.64 divided by 5 is going to give us that same 0.5 something. And truthfully here, what I'm getting as numbers is 0.528, and I got 0.51 before. It's the more numbers you keep, the less rounding errors, right? So I'm going to say the more numbers you keep, the better. So the less rounding errors there will be. Now, I mentioned that if I was doing this question from scratch right now, I probably would have a little bit of different numbers here and there, like the 0.66, for example. My 2.64, even in the first place, I might have had more decimals, and then when I divide by 4, I might have had more decimals on the 0.66, which would give me, so it's okay to have little rounding errors. It's like basically approximately, like maybe at this point we're like, okay, it's basically a half an amp, and this is still basically a half an amp. And this is basically 0.7 of an amp or something, you know what I mean? There are some rounding errors, and that's okay. All right, okay, for you when you're writing the quiz and the test and assignments and so on too, and when I'm marking it, a little bit of rounding errors is okay. I look at what you did to get them, and if what you did to get them is right, then you get the marks. I wonder though if that's going to be as much of an issue as it has in the past. It was a bit hard for me to mark before, right? Because I'd have to gauge, okay, is that a reasonable amount? And I'd fire some numbers into the calculator and I'd see what you got, right? And how you got it. I wonder if we start keeping 5 or 6 or 7 decimal places all the time. I suspect we're probably going to get the same answer regardless of how we go about calculating it, because this is now saying the current is 0.528, because I calculated it in a different way. But bothersome, but actually it's okay, basically is what I'm trying to get at. So now what we're saying is we know the current that goes through the 3 and the 2 ohm, right? So it's the approximately 0.5 of an amp or 0.51 or 0.53, whatever your calculations led to. So you calculate the voltages, and then we're done, right? That means we know the voltage and the current everywhere. Just give you a bit of time to get that part.
Right. Why again is the current through the first branch going through the I'm sorry, I think I didn't understand that.
Do you still have a question, or did you sort yourself out?
No. Why do you use the 0.51 there?
So the 0.51 was what we calculated as the current that's going through this top branch, right? Because we had 0.66 amps going through the bottom branch, right? Jumping back here for you. So that's 0.66 going through here. The remainder of the current goes through the top branch. And so if the remainder of a current of 0.51 amps is going through the top branch, then we know that current must go through both of these resistors. And that leads to the calculation on the next page where it's like, oh, so I know the current goes through both of those, and so I can calculate the voltage across each one.
Oh, okay, I see that now. Thanks.
Oh, yeah, Grace. It's a lot, I know. Yeah. But it's kind of like when you get good at it and you start plugging away, it's kind of like a little puzzle, and you're like able to just sort of crack the code and figure out all the pieces. It can be, it's okay for it to be kind of fun to do that. You know, if you get good at it, you'd be like, I nailed it. You know, allow yourself to take a little bit of joy or satisfaction out of that, if that makes sense. Yeah, because it is a very systematic process that once you get it down pat, you know, you start to get good at it, and you can get any number you want from the circuit, which is pretty cool. Use the word cool being used very fast and loose in the context of a physics class. All right. What do I have here? Solving circuits. You don't know all the R values. Well, of course, that's we've already done that before, where it's like you're looking for missing pieces and so on. So this is kind of out of context here, actually. I'm gonna skip this part because we've already done that like crazy. So I think I'm done the combination circuit part as a lesson. This may or may not, you may or may not like the textbook version of the explanation. So I have the solution written out for this in the, do I have it written out in the, yeah, I do. I have it written out, 30 volts, 9 ohms. Yeah, so I've got the solution written out like I would show in the posted homework solutions, so you can help yourself with that one too. Plus, there's also like the textbook version of it, which isn't, I don't know if it's terrible or not, but like I don't like, for example, if they're starting with this. Like, why not just start with V equals IR and work your way towards what you need to work for, right? I guess you could at least start with this, and then if you're looking for current, solve it. But to me, I don't know what my solving is going to be until I plug numbers in. So when they plug the 18 volts in and the 9 ohms, to me, now it's obvious that I'm going to divide both sides by 9. Why bother with this before you even know what you need to do? That's the problem with the textbook way of doing it. Is they kind of look at what they need first, and then they write the textbook afterwards, and it makes it hard to follow, I find. Okay, so just use the formula, plug in the numbers, and solve it out. So I'm hesitant to even, next time around, I might not even leave these pages in here, because I don't want to encourage you to think that there's some magical, like, oh, I have to remember that I use I equals V over R in this case. Be like, no, you just use Ohm's law, plug in the numbers, solve. It makes it so much easier. Okay. So you've got the model problem worked out, plus you've got these two to try, and those solutions are all going to be posted as well. So questions at this point? Does that seem doable? With practice, you know, like with practice and repetition and using the solutions for help and that, and then asking for more help too this afternoon or tomorrow afternoon, you'll get there. It's very doable. So next is electric power. So we're ready to forge ahead with that.
Sure.
We looked at electric power briefly in that question earlier, where it was like thrown out in left field, right? So now we'll officially see that electric power equation, and we'll even understand why it's true. Okay, so we know the result, we've seen it already, but I'm not going to show it to you right now in case you forget, or just, you know, like we're developing it anyways, right? So electric power, first of all, let's remind ourselves from grade 11 that power is often referred to in watts, right? But it's really energy per time. It's energy per time. So I want to add that in here. So it's watts for sure, but you might remember that that was joules, right? It's energy per time. Energy per second. So if you have a light bulb that's a higher wattage bulb, it's using more energy per second. Makes sense, right? So we're using our fundamental knowledge about power, being energy per time, as our starting point for figuring out the equation with electricity, like for electrical power. Okay, so we're starting with a known relationship, a known concept, and then building the new one from it. Rate of transfer of energy, right? Just give you a little bit of time to write down and digest that. All right, so should be enough time, I think. Let me know if you need more. So we need to think about the concepts to do with electricity. What concept in electricity is to do with energy, delta E, and so on? What's the big concept in electricity that's to do with energy? Anybody? Give you a hint. It's really the same as to do with like energy per coulomb. Like it's how many joules each coulomb is carrying in a circuit because of what in a circuit. What's giving electrons energy in a circuit?
The voltage.
Voltage.
I was hoping, yeah, I was looking for voltage for sure. I thought maybe at that point with the hint, someone might have said, well, the battery's giving the energy to the circuit. So then it's like voltage, right? That batteries have voltage. So we've got voltage as a concept. And then the other one that we have to think about is time. And the equation that we had to do with time was to do with how long it takes for electrons to flow and so on. So that's current. Okay. So we're going to use the voltage equation and the current equation. Okay. So we want, of course, to be able to put, let me just circle here. We want to be able to put delta E from this one into the equation, and we want to be able to put, let's go with a different color here, maybe delta T from this equation into there. Right? We're substituting known relationships into well, we have 3 known relationships, and we're substituting these 2 electric ones into this familiar power one from grade 11. Right? So that means I'm going to solve for delta E in this one and get Q times voltage. So the amount of charge times the voltage is going to go in the top soon, right? So we're just solving for delta E, and then we're going to put it in as my arrows show. This one, we're going to solve for delta T. So, mathematically, I'm going to multiply both sides by delta T, and then I'm going to have to divide both sides by I. So it's not super difficult math here. It's just sort of recognizing concepts that what you need to do, right? So that gave me a delta T equals a Q over it's like the amount of charge divided by current. Right? So that means that this one goes in the top and this one goes in the bottom. And that's what we're going to do in the next page. Let's actually put those in. So make sure you have enough time to follow that.
Could you just scroll up to the top for a quick second? Sorry.
Sure. Yeah. And I'm gonna be putting an equation in soon here too, right? So you're not behind if that's what you're thinking of, but is that enough time for those little bits of solving there?
Yeah, that's good, thanks.
So QV is gonna go in the top, Q over I is gonna go in the bottom. So boom, there they are. All right. And then luckily you paid close attention in math class when they talked about how you divide by a fraction, which is you invert and multiply, right? That gives you the equivalent mathematical result. So there's my invert and multiply. And then notice I've got a Q on the top and a Q on the bottom. Q divided by Q, Q goes into Q once. So just a 1, right? So a 1 VI is really what we're looking for there. And boom, we got it. There's the electrical power in watts. There's our voltage in volts and our current in amps, right? So if we look at our units here, this is actually, I suppose, amperage. I should have put an A there if I was talking about units. Notice that the unit analysis here is this is joules per coulomb, and then this one is coulombs per second. And so units wise, we're talking about joules per second, which is watts. So it all makes sense. E equals VI, power equals voltage times current, really does give you the power rating of a device. Voltage times current gives you power.
Do you mind scrolling to the top again?
Not at all.
Thanks.
Yep. You can almost see all of it there. So are we good on that page then?
I think so.
I think so. So that's you've seen maybe a similar proof before. Like I think when we did kinetic energy, 1/2 mv squared in grade 11, it was a similar kind of development where it's like, oh, I know force equals mass times acceleration, and acceleration is delta v over delta t, and blah blah blah. And you just put known concepts together and get an equation. So this might be your second equation development, where it's like I know 3 different concepts and put 2 into one and get a new concept. And for now, I want you to look at it as you can look at it and assess for yourself whether or not I've done anything wrong, right? You look at that and be like, yeah, that makes sense. I agree with that step. There's nothing wrong done here. And so what that leads to is then you saying, okay, so I can now say I have personally verified that power equals voltage times current, right? Because previous known concepts combined in a logical way to produce it. So that's where I want you to be at, is where you can say, yeah, I followed this, it makes sense to me, and so on. I am not necessarily saying that you would have started from scratch on a blank page and done this yourself, because like let's face it, that's what George Ohm and whoever's name would be to do with this equation did back in the day, and that'd be tough. That'd be creating something from scratch, whereas this is sort of analyzing and assessing the validity of something that someone else created. So that's 2 very different skills. So don't be too afraid of this idea here. I'm not asking you to do this stuff from scratch yet, right? That's kind of the next step, is being able to prove equations yourself. So now we're going to play around with this new equation and calculate things, right? So if we have a 60-watt light bulb that's designed to be used in a 120-volt circuit, what can we figure out? Well, we can figure out how much current actually flows, right? So that's pretty easy. You just plug in numbers. I'll give you a little bit of time because you're just getting started here, I know. On this page, you gotta spend a lot of time drawing a nice light bulb, of course. I'm joking. Makes it look good on my page, though. So it's kind of neat, right? We can actually calculate how much current is flowing in your household circuit. You got a 60-watt bulb plugged in and a lamp in the living room. You can actually calculate and know that that thing is drawing 0.5 of an amp. Okay. So just a related story to do with this. There was a time when friends of ours and there was like 3 different groups of friends maybe, that were kind of playing pranks on each other. And so we went over to this other friend's house, and it was around Christmas time, so we put up, we hooked up a whole bunch of Christmas lights on their front deck. Like we had all these extra Christmas lights. We just lit up their house like a Christmas tree on the front deck, right? As a fun thing. So when they turned them on, I guess when they turned them on later on, the fuse blew, right? Not fuse, but the circuit breaker that protects the circuit. So if there's too much current flowing. And so when I did the math on it, I was like, wait, each little Christmas light bulb drew like whatever it was, like 0.2 of an amp, or I forget what wattage the bulbs were, but I was able to calculate how much current they draw. And then I added it up and I was like, okay, we plugged in like 400 lights. That meant that circuit was trying to provide like 40 amps of current or something, right? And so of course it blew the circuit breaker. And not only that, they had their hot tub in the backyard plugged into that same circuit. And so when we went to the Christmas party 2 days later, it was discovered that the hot tub had been off for the last couple of days, and so it was really cold. And so there's maybe there's some boiling of pots of water and adding to the hot tub to try and get it up to temperature. But it was like as soon as I heard that when I realized the hot tub was not on, and then I realized it was on the same circuit, like, I think I know why that might have been. I don't know if they know about that actually to this day. I'll have to ask Mrs. Horn. Anyways, so that bulb is designed to have a certain amount of resistance. Think of this, okay? This bulb is designed, engineered, so that this filament here, tungsten filament, has a certain amount of resistance, right? So that it'll allow 0.5 amps to flow. Are you curious? I think you should be curious and be like, hey, we can figure out how much resistance that really is. How would we do that? Think of what we know here as a given information thing. We've got voltage. Go ahead.
I said use Ohm's law.
You got it. Piece of cake, right? So you want to know the resistance? Use Ohm's law. Good. There we go. All right. So that is, of course, if we're looking for the resistance, we can use Ohm's law. And so V equals IR, plug in the voltage and the current, and you can see that a 60 watt bulb has 240 ohms of resistance. And that's something you could actually test. If you have a digital multimeter in your house, you can set it to the resistance setting, take a 60 watt bulb, put the two wires, one connecting to here and one connecting to the end with a digital multimeter here, and it'll actually read 240 ohms. So it's kind of neat to see that in action. That actually does work. If I had an easier way to, I wonder if I could do that quick while you're writing. When you're writing a bigger section and waiting, I might grab my ohm meter and a light bulb and try and show you. For now, am I waiting right now, or are we good to move on?
I think good to move on.
We're good.
All right, perfect. All right, so compared to a 120 watt floodlight, what has to happen for this thing to be able to kick off 120 watts of power, 120 joules every second, instead of, in comparison to this one, only kicks off 60 joules every second, or uses 60 joules every second? What has to be different about this one in order to have it be more powerful? It has to let what amount of current through? More or less, of course, for now. We know it has to let
more current.
More current through, perfect. Right? So if it has to let more current through, then this big, really bright floodlight has to have what for resistance? If it has to let more current through, it actually has to have less resistance, right? We talked about this before. So it has to let more coulombs through because each is going to be carrying a certain amount of energy. And so we can calculate how much current it lets through. So it lets through 1 amp, which kind of makes sense, right? It's double the current to get double the energy. So for now, that's making sense because we're not changing the voltage. You're going to see something weird in this lesson about when you have different voltages. Anyway, so we get the 1 amp, and then we calculate the current, and we see that it has only 120 ohms, which is less than the 60 watt bulb, of course, in order to let more current through. I'm going to gather equipment here while you're writing that. Let's see if we can pull this off here. So let's just turn on the camera here. I'll have to get rid of my background. It's probably on there still. Just remember it was in here. Device settings, was it? No, it was apply background settings or something like that, wasn't it? None. That's what it was. There we go. So I'm not getting the same numbers I thought I would, but this is the digital multimeter. And if you hold it there, you can see it's saying like a 1 right now because it's basically like infinite resistance. And the hard part about this is to try and show, but you know, if I have the bulb, I'm going to put the wires to the 2 parts here. I can't do this with only one hand. Free here. Here we go. So I got the wires on there like that. And then you can see it's reading, this one's reading 22 point, is it backwards? Yeah, it's backwards, isn't it? It's inverted. So that number is hard for you to read, but it's actually 21. So this bulb is, it says it's 60 watts, but its gut reading is 21 ohms, which the resistance, you know, it's probably a non-ohmic thing, actually, thinking of it, because when the voltage starts to apply on that, I bet you the resistance changes and increases a lot or something changes about it, because that's not the right resistance value for that wattage of bulb based on the voltage, but we're not applying 120 volts onto it right now, and so I bet the resistance changes when the voltage applies onto it. But that's the idea of, you know, you can actually just check to see the resistance values. So a little bit of real life dose of reality there, where it's not necessarily the exact number you might expect because things change when voltage is applied. Anyways, so calculating electric power. What's the power rating of a segment of nichrome wire if it draws 2.5 amps and connected to a 12-volt battery? You know, this one's pretty simple, where you're just like, okay, I've got current, I've got voltage, I can figure out the power, right? Boom, boom, boom. I'm not even like, I don't even think we're gonna leave this long enough for you to write this down. That's way too easy of an example. Just plug it in. Okay, let's focus on bigger and better things. Oh, this is a kind of a neat application section here. Something that maybe isn't as common anymore, because inverters and you know, devices that can take a 12-volt battery voltage and then convert it to be 120 volts are way more available, way more common, and less expensive now. So people might not do this as much. But when my parents bought their cottage, or campus, it's called in Northern Ontario, they wanted to wire it up so they could have lights flipping on with a switch, but they didn't have hydroelectric hooked up there, right? They still don't. So they wired it up as 12 volt. And you know, if you're wiring up a cottage with 12 volt wiring, do you think the wires should be thicker or thinner than normal house wires? So you're going to try and use a 12 volt source, a whole bunch of 12 volt batteries hooked up to be able to provide enough energy to be able to make light bulbs run, and you know, other small appliances that can run on 12 volts anyways run. Do you think they should use thicker or thinner than normal wires? So it's a bit of a guess there, and I won't subject you to having to guess, but I think maybe a lot of people might think thinner because it's only 12 volts, not that dangerous, no big deal, right? In actuality, the problem is the 12 volt system is only delivering 12 joules per coulomb, right? That's not very much energy. So a ton, like 10 times as much current has to flow in order to deliver the same amount of energy. If 10 times as much current has to flow, now it's more obvious. The wires need to be thicker or thinner to allow that. They need to be thicker. You follow me, right? So the wires need to be thicker so they have less resistance to allow all of that current to flow, right? So there is some resistance in the wires themselves. And so if you're using like regular household wiring, like just you know, 12 gauge, 14 gauge is really most common. The resistance in those wires would actually be a factor, and they would get warm. Those wires in your walls, which are made of wood, would get warm. It's not the best plan, right? So there are bulbs that are designed to be used in a 12 volt circuit. You can go to specialty stores or whatever, hardware stores don't typically carry them, but you know, a 60 watt bulb, it's designed to look and act like a 60 watt bulb, but it's designed for use in a 12 volt circuit. It would be designed to have less resistance to allow more current to be able to get enough energy, if you follow me. All right, so you can calculate it out. You'd be like, oh, so you have the 60 watts, you'd have the 12 volts. It wants 5 amps flowing, right? Just for one light bulb, 5 amps. That's like a half or a third of a normal household circuit just for one light bulb. It's a lot of current, all right? There's that 10 times as much current. And of course, we can calculate the resistance. So it only has 2.4 ohms. So it allows a lot. It allows a lot more current. Okay. So this, notice this this resistance here, instead of being 240, right? 240 divide by 10 again, we're ending up with 2.4 ohms. There's a double, there's a 2 factors of 10 less in this, because we have 10 times less. We have a divide by 10 in voltage, right? And then we have, as a result, we have a factor of 10 difference with the current as well, right? So we have 10 times as much current flowing, and then they're carrying, you know, 10 times less energy, and so there's a double factor of 10. You'll see that in a couple different questions when we go through this. So 10 times less voltage, it should be saying, right? And then, yeah, anyways, does that make sense? All right, so we'll do that a couple more times here to get the hang of it. What do I have here? Oh, if you were to try to use a standard 120 volt bulb in a cottage circuit, you know, would you want to use, do you think you should, these are all like little thinking, problem solving kind of questions, right? So if you were to take a standard light bulb from a regular house and try to hook it up in a cottage, which one would have a chance of working? Would you want to use a higher wattage than normal bulb or a lower wattage than normal bulb? And remember, you have to have less resistance here, right? For in the cottage to be able to let enough current flow through. Which bulbs have less resistance? The ones with higher wattage, right? And so you use a way, if you could find a way higher wattage bulb, you might be able to use it and it might glow a bit, right? So for example, if we just chose a 60 watt bulb, which isn't high enough, but if just do the numbers for a 60 watt since it's here and ready to go, right? We have the 240 ohm. How much current will actually flow? Just use Ohm's law, of course, right? So you can see the calculations here. We can get 0.05, right? 0.05 amps will actually flow. What you notice is 10 times less current. Not only do you have 10 times less current, but the energy they're carrying is also 10 times less, right? And so how many watts will this bulb kick out? If it's getting 10 times less current, each coulomb in that current carrying 10 times less energy. We've got a double factor of 10 less. So that drops us to 6 watts and then down to 0.6 watts, doesn't it? So you can kind of predict based on logic what wattage this bulb would actually behave as. So I put plus, they're carrying 10 times less energy. And so here we end up with 0.6 watts. If you hooked up a 60 watt bulb, it probably wouldn't even glow. 0.6 watts is going to be going through it. You're wasting energy because it's really not even glowing at that point. Okay. So I was at the first house we lived in the area. We had this tiny little water heater, because it was a super small house, and so this tiny little water heater it was hooked up with 120 volt. And so I wanted to increase the capacity of this thing. I wanted to reheat quicker. And on the side of the the electrical tags, we're gonna talk about electrical tags in this lesson soon actually, but on the electrical tag for it, kind of indicated that it's like if it was 120 volts, it's a 1500 watt heater, and if it's a 240 volt, right, which is the other kind of circuit you can have in a house. Let me just remind you that you have like a plus 120 line coming into your house, and if you connect to ground, then you've got 120 volts, right? So that's supposed to say 120 there. Just to go along with this story, I have to tell you a little bit. So this is 120. So you'd have obviously 120 volts, right? But you also have into your house a minus 120 volt. So it's just 120 volts opposite phase. So this one's like this and the other one's like this, you know, whatever. So if you connect this wire to this wire, then for your circuit, you're actually getting 240 volts, right? So you have 120 and you have 240 available in your house. So for this hot water heater, I was looking at it and it said like, oh, it kind of almost looked like you could hook it up either way, right? And so if you hook it up with 120, you're getting 1500 watt. If you hook it up with 240, you're getting 3000 watt, double the power because it double the voltage. So I wasn't thinking very clearly. And so I hooked it up to try it because you know what? I was basically honestly thinking, I don't think this will work. I didn't bother to do the math or the physics of it, which I totally could have, but I just didn't bother because I was pretty much just planning on changing the heater, the element anyways. You can just 2 volts, take it out, put a new one in, right? So I just hooked it up with 240 to see what happened. Well, what happened? Of course, it stopped working immediately, completely stopped working. Why? Is it obvious why it didn't work and how I should have known? When the side of the tank says, oh, at 120 volts, you're getting 1500 watts. And at 240, it's functioning as a 3000 watt. What's wrong with the math here? Why should I have known, even looking at that label, that that element wouldn't work properly? So what I'm hoping you're going to be able to tell me soon. In a class setting, I think I would probably have more patience waiting for an explanation here, but this would cause twice as much current, right? Which, if that's all that was happening, if it just caused twice the current, you'd get twice the power, and that would make sense. But we have also, right, the electrons carry twice as much energy. So what wattage, this is not, oh boy, twice the energy. So what wattage did my heating element in that hot water heater try to function as? It tried to function as a 1500 times 2 right here and times 2 again right there. So it tried to operate as a 6000 watt element is what it tried to do for about a half a second, and then it obviously just burnt out and stopped working completely. Okay, which I should have known. I could have known. If I had have thought about it at all, I would have looked at it and went, oh, that the math doesn't make sense on that one. You can't just hook it up with 120 or 240 and think it's going to be double the power. It would actually be 4 times as much power. Okay, because you're getting double current plus those electrons are carrying double energy. It's a double if you're a Tim Hortons fan. Okay, so that's something that comes up a lot when you're thinking through, what happens and so on in circuits. In reality, what happened was I bought a new element that was designed for 240 volt, meaning it had higher resistance and had an appropriate resistance so that it allowed 3000 watts to be produced. Right, it was like $20. I put a new element in, and my end goal was achieved. We had a faster recovery time on this hot water heater because it was more powerful. But you couldn't accomplish it just by hooking up 240 volts. Okay. Yeah. So I was thinking of this a lot when I was hooking up the in-floor heating because we have in-floor heating in 3 spots in our house. 2 of them are 120 volt. 1 of them is 240. And so when I was hooking up the 240, the third one I hooked up. It's a bigger area, right? So I needed more power. So I thought, okay, I'll have less current if I use a higher voltage. But I was definitely double and triple checking and be like, this does work, right? I can, there's 2 different connecting spots in the box. And so it's designed to actually be hooked up with one or the other. but I was definitely not wanting to fry the in-floor heating that's underneath the tile that I had just put down. Anyways, so you can see this stuff has got some real life skill connection. If you remember to actually calculate it, I suppose. Anyways, it is what it is. That cottage bulb, that special 12 volt, 60 watt bulb, if I hooked it up in a 120 by accident, if you took the cottage bulbs home, put them in a box, and then hooked it up at home, what would it try and behave as? Any predictions? What would a 12 volt, 60 watt bulb try to behave as if you hooked it up in a 120 watt? So you've got 10 times as much current, and each of those electrons in that current is carrying 10 times as much energy. What wattage would that bulb try to behave as? This should be doable. Like, this is something, if you're not able to follow this with me, you need to ask questions. So let me itemize this out for you again here. Is my mic still working? Yes, it's working.
Yeah, it's working.
10 times as much voltage is going to lead to times 10 as much current, times 10 current, and right, plus we have 10 times as much energy. And so we're talking about times 10 times 10. You should be predicting that this thing's going to try and behave as a 6,000 watt bulb. You plug in this light bulb thinking it's going to work. It just looks like a light bulb, right? Plug it in and immediately it burns out. Gives a big flash of light, but of course melts the filament inside instantly, right? Because we have this 10 times as much current flowing, so it's going to try and draw 50 amps. And so if the bulb didn't melt instantly, which is what would happen, instead the circuit breaker in your house would blow, because the circuit breaker is not going to allow 50 amps, right? They only allow 15 to 20 amps. So the circuit breaker would blow right away to stop the current, so much current from flowing through your wires and your walls, and you don't want the house wiring in your walls to catch on fire. So obviously the bulb would not sustain this. But the kind of calculation we're doing here, the idea of this, times 10 times 10 is a very, very valuable piece of knowledge to do with electricity and how it works. Okay, save yourself the frying a heater element in your water heater and stuff like that. So related to this, of course, people go on trips. Once the pandemic's over, people will start going on trips again, right? Europe is wired at 240 instead of 120, right? I've talked about this in the past in grade 9 science and in grade 11 physics, but some years. So it was wired afterwards. And so this is what scientists from North America recommended Europe do, right? North America wired first. We went with 120 because our switches weren't great yet. We didn't want to burn down people's houses. And so we went with 120 to be a little safer, but we found we need more power. And so we recommended going with 240 in Europe. So the question is, of course, what happens if you plug in a device, right, from Canada on your trip? You plug in without any kind of special adapter to convert the voltages. We'll talk about how converting voltages works in this course. But for now, if we just plugged it in, what would happen? You plug in your phone, let's say in Europe, and it's supposed to draw like 1 amp. Well, now instead it's drawing 2 amps. And not only that, but the energy being delivered to your phone is twice as much. So instead of it charging at the rate that it's supposed to charge at, it's going to charge at a rate that is, right, 4 times faster than it's supposed to. You're supposed to have maybe a 1 or let's say 2 watt charging rate. Instead, it's going to be times 2 is 4, times 2 is 8. It's going to try to charge at 8 watts. That's not good for your phone.
Why is it 4 times as much and not just 2 times as much?
Well, because of this idea here that the 10 times the voltage is going to cause 10 times as much current, right? So you have 10 times as much current, but you have to remember that each coulomb going through, there's 10 times as many coulombs going through, right? Each one of those is going to carry 10 times as much energy. So instead of one set of 1 volt, let's say, instead of one set of 2 volts, right, you're going to get 10 sets of 20 volts. Right, so you're getting a double multiplication there. You're getting a multiplication on the current, plus also you're getting a multiplication on how much energy the electrons actually carry. Does that make sense?
Yeah, thanks.
Yeah, so in Europe, you're going to have twice the voltage, right? Which was going to make twice as much current flow. But coupled with that, each electron that flows, twice as many are flowing, right? Each one of those is going to carry double the energy. So it's a double-double situation. So here's an example to help see this again, right? If you have a 1200 watt hair dryer, I have one of these in 124, which I normally show in this lesson. So power equals voltage times current, right? We know it's designed to be used in a 120 volt circuit. And so we can calculate out that's going to draw 10 amps, right? You can't plug in like 6 hair dryers at once, you know, in a bathroom. Like it's, you know, or even 2, you probably can't get away with. 2 hair dryers probably blows the circuit because they're drawing like 10 amps, right? So 10 amps, we can calculate how many ohms that is. So I'm just using the power equation, and then I'm using Ohm's law. Okay. So if you brought that hair dryer to Europe and just connected it and see what happens, right? This is what would happen. You'd be like connecting 240 volts to a 12 ohm resistor. And so it's going to allow 20 amps. So that's where we're talking about. This is double current, right? And then we're realizing, oh, wait, double current. But on top of that, we're getting double the energy as well, right? So this right here, let me just draw an arrow in here. So with double current, I can say, and we have in here double energy. So there's your double double. Very more obviously worked out on this page for you if that helps. So there you're getting now. Just reset my computer here. I can change things. Seriously. I'm a crazy computer. So that hair dryer would try to operate as a 4,800 watt hair dryer, right? That's if you're just using a connector that, you know, basically makes it so you can put the 3-prong style we have in North America into a 3 style that they have, 3-prong style they have set up in Europe. Okay, so if you're just connecting the wires and not changing the voltage, then it's going to try to operate as a 4,800 watt hair dryer. Is that going to work? Is this thing going to work properly? No, it's going to either blow a circuit or it's going to melt, or it's going to stop working. Probably a little puff of smoke comes out and then you're done. Okay. If you transform the voltage down to 120, great, that's fine. Then it'll just work like normal, right? But it would melt trying to give off 4,800 watts of hair frying power. So Paige, I think you had asked about the why it's double double. Does that make sense more now?
Yeah, thank you.
Perfect. My pleasure. All right. So there's again, it's more fun to show this in person there, but the hair dryer that I have in 124 has a little switch, and it says it has a little 120 240 switch. What does it do? It actually just restricts the hair dryer to only be able to access the low power setting. So when you flip it to 240, the high-low setting on the hair dryer doesn't work anymore. It's locked into low only. You can only access the low power, which makes sense because the low power setting in Canada, right, is higher resistance, so that it lets less energy go through, right? When plugged into 240, it'll actually produce full power because the less current flowing will carry enough energy to actually power it fully. So if we look at this, the way the numbers would work here, so the resistance needed, I'm asking what resistance should that low power setting be so that when you hook it up in Europe directly to 240, it would actually produce the high power setting. Okay, so let's look at the power amount that we want, right? So basically we want this much current. So if I know how much power I want and I know the voltage, I can look at how much current I want. I want 5 amps, right? So then if I want 5 amps, then I can figure out how much resistance. Right? So I have 240 volts and I want 5 amps, I can figure out what resistance. And so if you made the resistance be 48 ohms, then the low power setting, right, that's more resistance than the regular setting. The regular setting was, go to my hairdryer here, regular resistance was 12 ohms, right? So we're saying if we make the low power be 48 ohms, then it would be low here in North America, certainly, right? Nice to have a low setting and a high setting. But that low setting would function the same as the high setting when plugged in Europe. So basically now they can look at what wattage, what power rating this low setting would be in Canada. Okay, so obviously we're going to, let's say let's just point out what we would choose here to help you realize that this is doable, right? So you're saying, okay, I've got a resistance of 48 ohms, I've got a voltage of 120 volts, and I want to know, what can I figure out? What can I figure out? I can figure out the current, right? V equals IR, Ohm's law. So that's what we're going to do. Plug in the numbers, calculate for the current. So in North America, that low setting is going to allow 2.5 amps. Right? And of course, now we've got voltage and current, so we can calculate how much power. So that low setting is a 1200 watt hairdryer. The low setting, if they want it to function the same as the high setting, right, would actually only be 300 watts. So it's kind of a slick way that the engineers designed that hairdryer. I think, it's kind of neat, right? The engineers probably told the people selling the hairdryer, they're being paid as the science knowledge people, right? And they're like, well, if we just lock out this switch, then the low will function as the high power. And people that run the company are like, okay, I'll take your word for it because I don't understand that physics, but the physicist gets paid the money to help design these things. In which case, that physicist is working as an engineer, solving problems using physics. Okay. All right, so that's a very common, thing to be able to sort of think through and calculate and so on. This one I might just reveal it and then you can look through it again your own. But this is just a kettle, 1500 watt, 120 volt. What's the resistance of the heating element? And what's the power output, and so on. Now this question here is, it's not just that it's going to be a little bit less, right? It's going to be less by double. Now, it's hard to do the math for this one because 120 down to 108, it's not like we've fallen and we've lost half the voltage or something, or 10 times less voltage, right? So we have this like 120 down to 108 is sort of a not easy to picture decrease. But certainly we can calculate how much current it draws, and we can calculate how much resistance it draws, and go through these later and make sure this works for you and makes sense, right? But the tricky part, that's the easy part. The tricky part is if it drops to 108, then of course you have to figure out, okay, well, how much current will there be now? And then after that, calculate how much power there will be. And it's pretty straightforward. You just look at, how much current there would now be, right? So there's less current. So I'm going to point that out here. I'm going to point out that this is less current. And then plus, right? Plus on top of that, notice that there's going to be less energy per coulomb. So, you got less energy per coulomb plus less coulombs flowing. And that's that double decrease business going on again. Set my screen here, hopefully. There we go, maybe. So yeah, so that's actually going to lead to this thing being 1,215 watts instead of 1,500 watts. So that's my note there about less current plus, I guess I wrote the double twice. I see the irony. Okay. Just a note about this double thing here. Like you can see the voltage is 0.9 is what that works out to. This is similar to that ratio work that I showed you earlier on, right? If we want to know what multiple that is, second divided by first. So it's times 0.9, which means 10% less, right? So we've got 10% less voltage, resulting in 10% less current, as well as the energy they have is 10% less. So you've got a double 10% drop. It works out. You've got the 120 times 10%, or like reduced by 10%. We've got the current reduced by 10%, and it gives us that correct power rating. So this is a good page for describing why it's a double reduction. So we've done 3, I think, of those now, double reduction analysis. So I think we'll leave the rest for you to work out on your own for that. I'll jump ahead to, oh yeah, okay. I'm just gonna show this fairly quick. Maybe I'll come back to this one. I'm gonna come back to that one. I just want to show you something neat first. CSA tags. So if you look at any device that uses electricity that's certified for use in Canada by the CSA, Canadian Standards Association, they're going to have information listed on it. So this is the back of the microwave that's in the math office. Says 120 volts, and it says 600 watts. It says 600 watts. It has some other information too, like it's designed for use in a 60 hertz circuit. Europe, I think, wired in 50 hertz for some reason. There's really no reason for them to have a different frequency. It just makes it more complicated for adapting between the two, which is ridiculous. But those are the main pieces of information they give you. And the neat thing is that on all these CSA tags, there's always going to be like one thing missing. And so our new knowledge of electricity allows us to solve for missing info. And so you actually have a whole bunch of little physics questions around your house. Just look at the CSA tag info on the back of your printer, the adapter for your printer, the adapter for your computer, the label on the bottom of your toaster, every device that plugs in will on somewhere on it have information, but they always leave something out. They almost at least always leave something out. So here we've got voltage and we've got wattage. We can figure out the missing piece, which would be, obviously they gave us V and they gave us power. So V and P, well, we know P equals VI, right? So we can figure out the current that this microwave would draw, right? Boom, there it is. So you can calculate that it would draw 5 amps. So you could run 2 of these microwaves at once on a regular circuit. The 2 microwaves that are in the staff room, on the other hand, can't run at the same time because they are more powerful. They're like 1200 watt microwaves, so they presumably draw about 10 amps, the same voltage, right? So it's only one increase. So they draw 10 amps. So if you try and run 2 at once, they take 20 amps, and it blows the circuit breaker. The other thing we could figure out if we wanted to would be what the internal resistance is of this device. You put voltage on it, a certain amount of current flows, obviously it has a certain amount of resistance, right? So we could figure that out too, which would just be Ohm's law. Right, so Ohm's law, voltage and current, you just calculate the resistance. So every device, I've got a whole bunch here, like this is the adapter for a laptop charge cable. Notice it gives 120 volts and 36 watts. That's the input, okay? So the input is 120 volts, 36 watts. So we can calculate the current, right? How much current is necessary for, power. This is power, this is voltage, we can figure out current. So let's do that, right? P equals VI, plug the numbers in, it says 0.3 amps, right? 0.3 amps input because power equals voltage times current, right? Something a little weird about this, if you notice, I could point out to this is the output power. So the output power is 18 and they gave the voltage and the amperage for some reason. So this thing puts out 27 watts, right? Takes in 36 watts, puts out 27 watts. Where did the rest go? So coulombs are bringing in 30, whatever. It's using 36 joules per second, but only effectively providing 27 joules per second. Where did the missing 9 joules per second go? Any guesses? We're losing energy somewhere. Give you a hint. Have you ever felt one of these adapters that are plugged in your house?
Does it come in heat?
It sure does. They're warm, right? So if you leave a computer cord plugged in all the time at your house, I do it myself. But it's silly because they are using power just being plugged in, just sitting there being plugged in. They're using power. This thing's using almost 9 watts. That's as much as a regular light bulb now. The LED light bulbs use 9 watts. Are you going to leave the light on in your bathroom all the time? Most people don't. Most people turn them off once in a while, right, to save energy. So you're all these devices that are plugged in, printers, laptops, even TVs, to be honest, like things that are just left plugged in all the time. They call them like a ghost draw. They're always drawing energy. You can see this, the efficiency number from previous work in physics as well. You know, if it's giving off 27, but you provided 36, this thing's only 75% efficient. That seems low to me, to be honest, knowing that this is really just a transformer. They're usually more efficient than that. So the other thing I want to sort of point out that should be kind of weird to you, looking at it, is we have 1.3 amps coming in, and we have this question down here. We have 1.5 amps going out. How can it take in 0.3 amps and give off 1.5 amps? Doesn't seem possible, does it? But it actually is possible. So later on, when we learn about transformers, that'll actually make more sense. We'll be able to justify how that's even physically possible. Okay, transformers are the key for that one. Spoiler alert, what it does is it transforms high voltage with low current, a certain amount of power, of course, right, to being high current with low power, right? So it converts between the two, between voltage and current. That's what transformers do. But we're going to see how they do it. They're actually really, really, really easy to understand. So here's a kettle with the tags, the information we can calculate. Here's a, so I'd really like to have you go around your house and find some devices. There's the bottom of a toaster. It's a little hard to read, but when I zoomed in, I can see that it says it's 120 volts at 900 watts. You can calculate the missing current and then the missing resistance values. There's a carpet cleaner, just to get you thinking about all the different things you could find around your house. Okay, carpet cleaner, 120 volts, 2.75 amps. They don't tell you the power of this thing, right? It doesn't say how many watts this thing is, but you can calculate it. This vacuum cleaner actually does say on it the wattage, and it gives the amperage. So it gives the wattage and the amperage. So that means that you could figure out the voltage it's meant to work at, I guess, really, and then figure out the resistance in it. I once tried to plug one of these into a car, the 110 outlet on the car, and if you do the math, it was trying to draw 105 amps. So it's like, since the fuse in the vehicle is only 20 amps, I don't think that's going to work, right? I once wondered if it could, so I looked into it, of course, and determined in that case that it didn't make sense to try and plug it in. But these are just many, many, many examples here. So if you should be able to find some anyways in your house, but if you don't, use some of these. But like there's easy to find CSA tag info on every device. Okay. So that is the new info. I am going to, at least for now, I'm trying to decide if I'll cover it at all in this class. But I don't feel it's necessary to cover the cost of electricity stuff, but it would have been looked at in grade 9 science. I had it as a review here, and there's questions on the bottom of this sheet. But for now, at the very least, we're not going to do that part, at least for now. So on your handout sheet, you can, not to do those ones, because I have told you now here. Just bear with me for a second. There's something else I had to show on that sheet, I think. Nope, actually, no, we're good. I think we're good. I thought there was something that I had to correct or something but it was the other sheets I'm thinking of where the ABC was in a weird spot and so on. So the solutions for these, when you're going through these questions, I want to point out one thing actually. Just remembered. I think one of them it starts out with is harder. Like if you look at question 40, where is it? Question 40, for example. Like question 40 is harder because you have to use the power and the voltage question, or in the question, in comparison to which one. So they're not necessarily in a good order, basically. Some of the questions you just use power and the power equation directly. So just be aware of that, okay? Just the idea of using both equations, use one and then the other, like we've been doing. It comes up a lot in these. Okay. So I would definitely classify these questions as, you know, a fair bit of work, more than just one day's worth. And so it actually works out well timing wise that I'm not running a lesson tomorrow, because it gives you an extra day to plug away at these, look at the solutions, learn from it, get through the hurdles along the way to get good at it, and gives you some time to make that a reasonable task. So questions? All right, no questions. So I'm going to stop the recording so I don't forget. And